Hi, in the last session, we have explored the principles behind the QoS in 4G and 5G. We understand that how the network manages different type of traffic to ensure the appropriate level of services for various applications. Now, in this session, we will see that how 5G quality of services meet the requirements of massive machine type communication or MMTC use cases in 5G. Massive Machine Type Communications or MMTC is one of the segments from three major use cases of 5G. It refers to connect a large number of devices like up to 50,000 devices per cell. These devices are low cost devices and they are just designed to transmit very small amount of data. These devices needs longer battery life like up to 10 years on just couple of batteries, and they require strong coverage even in the challenging locations like buildings and basements because these devices can be placed at any point. We are needing such a low cost devices which also have longer battery life with extended coverage because these devices are supposed to send or receive very small amount of data just like a few hundred bytes per day. Currently, the demand of MMTC devices is met by two technologies, which was evolved from native 4G LTE network. And these are eMTC or CAT M1 and Narrowband IoT CAT NB1. The MMTC features based on 5G NR are still evolving. So, for the time being, these two technologies mainly cater the demand of MMTC use cases. Now, let's look at the key principle behind eMTC and Narrowband IoT. The first goal in MMTC is to design a low complexity and a low cost device. Devices that supported LTE Release 8 features were called Category 4 devices or Cat4 devices. These devices can achieve downlink speed of 150 Mbps and they are able to use 64 QAM modulation for downlink. And they also support 16 QAM modulation in uplink. They support 2 by 2 MIMO and they can utilize the bandwidth up to 20 MHz. And the transmit power is up to 23 dBm. For MMTC, we need devices that are simpler and cheaper. So, in later 3GPP releases, these features were scaled down to meet the MMTC requirements. In release 13, two specific technologies were introduced, eMTC or CAT M1 and Narrowband IoT or CAT NB1. Because MMTC devices sends very little data, so their peak data rates were reduced to under 1 Mbps for eMTC and a few hundred kilobits per second for Narrowband IoT. Also, the modulation schemes were limited to 16 QAM and QPSK. And because of these reductions, the complexity of the devices gets reduced and the cost is also significantly reduced. Additionally, there is no support of MIMO in these devices. These are only using one single transmit antenna and one receive antenna. And the bandwidth is also limited to 1 MHz for eMTC and 180 kHz for Narrowband IoT. And because of these narrow bandwidth, the receivers and transmitters become simple in design and they also consume less power. Additionally, the transmit power of these devices can optionally be reduced to 20 dBm, which ultimately helps in lowering the cost, complexity, and extend the battery life. Full duplex communication is also optional in eMTC technologies that also simplifies the design. The main difference between these two technologies is that CAT M1 mainly caters to devices that need significantly higher data rates or support for voice traffic as well, while Narrowband IoT is useful for the devices which require even lower data needs. By simplifying these features, the complexity of the devices is reduced nearly 15 to 20% of a typical LTE mobile broadband chipset. So, this approach allowed manufacturers to develop low cost and low complexity devices, very specific to the MMTC use cases. Now, the next question is how we can achieve long battery life for these devices. MMTC devices targeted to support up to 10 years of battery life with just couple of batteries. So in addition to have a low complexity modem, we have two more concepts to help improving the battery life. Let's look at them. Usually when a device sends some data, it normally enters into the connected mode to transmit the information and that required power. And once the data transfer is completed, then it moves into the ideal mode. And it also switches off its receivers to save power. But the problem is, if device is in sleep mode, then how the device will know that there is some data for it to receive? So it needs to check paging information. But instead of continuously looking for the paging information, the device only checks the paging information at some time interval. And for rest of the time, it goes into the ideal mode. This idea is called DRX or Discontinuous Reception, where the device checks for the paging information at some time intervals. In LTE, this DRX cycle is limited to 2.56 seconds. But because MMTC devices handles infrequent data, so they can even use longer DRX cycles to save power. This extended cycle is called eDRX or extended DRX. In eMTC, eDRX can be up to 43 minutes, and in Narrowband IoT, it can be up to 3 hours. With this extended DRX concept, devices check for their paging less frequently, which also help in saving the power. But what if the data is even less frequent? What if there is no data to check even for more than 3 hours? In such cases, the devices enters into the power saving mode or PSM, which is the second key feature. In PCM mode, the device enters into the power saving mode and it only consumes very least amount of power. In this power saving state, the mobile is registered in the network, but that does not monitor any paging information, and hence it becomes unreachable from the network point of view. Now, when the device wakes up after the agreed period, then it can send and receive the data again with the network. You will be wonder, but power saving mode can be used for up to 413 days, which is a significant amount of time. So together, eDRX and PSM techniques are helping to extend the battery life of MMTC devices. eDRX handles the interval up to 3 hours, and if the application can wait for the longer period, then the power saving mode can be used. Okay, now let's talk that how we can achieve extended coverage. eMTC offers up to 10 dB more coverage compared to the GPRS and Narrowband IoT, and it offers up to 20 dB more coverage than the GPRS. In both technologies, the key principle is to extend the transmission time by repeating the same packet multiple times. By repeating the same packet multiple times, receiver can accumulate more energy from each packet. This method can be used to extend the coverage by up to 20 dB. Means devices which are far from the base station, or if they are deep inside the building, they can still have possibilities to receive the signal. Narrowband IoT and eMTC can use up to 2048 repetitions in downlink and 128 repetitions in uplink data channels. The number of repetitions is determined by the device coverage. If it is in a bad coverage, then the transmissions will be more. If it is in a good radio condition, then the transmissions will be less. And because of these repetitions, eMTC can achieve up to 10 dB better coverage than the GPRS and 15 dB better coverage over the LTE. While Narrowband IoT can have up to 20 dB better coverage than the GPRS and 25 dB better coverage over LTE. In addition to this, there is a second aspect. Control channels can also be limiting factor in coverage. So the power levels of the control channels can also be increased to improve the coverage. But that need to be done very carefully and should only apply to those control channels which are the limiting factors of the coverage. So these are the two main techniques which can be used to improve coverage for MMTC devices. Now let's quickly see that how these technologies can be deployed on existing LTE networks. So eMTC can be directly multiplexed into the existing LTE carrier. You can see this in this picture here. For example, if there is a 20 MHz LTE carrier, a 1.4 MHz portion can be allocated for eMTC access. Even this chunk of spectrum can be time shared between eMTC and non-eMTC devices, depending on the traffic and uses. The rest of the spectrum can be used to serve the regular LTE traffic, like as usual. Similar deployments can also be applied to NR spectrum, as you can see here. However, Narrowband IoT supports even more flexible deployment. First, just like eMTC, it can be multiplexed into the LTE carrier. Additionally, it can also be deployed standalone in the guard band between two carriers. It can also be deployed as a completely standalone system with a dedicated spectrum. Narrowband IoT supports all these three types of deployment options. Well, regardless of choosing options, both of these technologies can seamlessly integrate into the existing LTE networks. They can provide MMTC based services, and depending on the traffic, it can do time sharing to share the load between LTE broadband and massive machine type communication use cases. Okay, so that's it for today. In the next session, we will be talking about 5G cell, and we will have some background on different concepts of a cell. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.